Okay, so moving on with this 6502 emulator. This time I probably just want to clean up some code and not write any new instructions or anything like that. Just try and fix a few of the problems that we picked up in the last video and try and just clean up a few things that have been pointed out. And one of them was pointed out by someone on YouTube, Costu96 or Costu96, butchering that name. He or she said, why have you put this WriteWord in the memory class and all the other read byte, read word, write byte are in the CPU class? And I think that is a good point. It seems a bit weird that really the memory class is just the memory and being able to actually access the bytes, and we'll need to put some asserts in there. So this thing probably shouldn't be here because it accesses this cycles thing, and really that's a CPU thing. So first thing I'm going to do is actually just move that into the CPU. This doesn't make too much difference, but yeah, it's probably, I mean, it makes sense that write byte should be next to WriteWord. And also, why did I make that a U32? Because an address is a word. It's, oh, I always put world. So yeah, we write the value, and also these things are all in some kind of odd order. So let's put them in the same order they are everywhere else. So let's have that taken in memory. So this kind of like matches up with what's going on in this one as well now. I think that's right. Yeah, I like the look of that. I think that's right. So and it's to memory, yeah, because this is the CPU doing this now. Cool, so let's see what that breaks. WriteWord is not a member of, oh, there you go. So I only used it in the JSR, and I haven't really kind of done anything with the JSR yet. And this is one of the things I did want to actually look at. So let's just see. So I can now just write word straight in here. Again, you can see this doesn't change too much because I'm writing word and taking the memory. I just need to get this stuff in the right order. It's the value, the cycles, the address, and the memory. So I don't think that changed anything because we haven't really worked on JSR, so it's not really in that great a shape yet. So everything carries on there because I don't think there's even a test for that. Make that a little bit tidier in there. Oh yeah, this was another thing. I had this fetch word function. It's fetching a word from memory, and this will be a word that's basically at the program, wherever the program counter is. So you access wherever the program counter is, and then you access the next byte. And I said here that, oh, if you want to handle Endianness, you would have to swap bytes here, but actually that's a lie, because we know that we're reading in this stuff from the memory. This is the memory of the virtual CPU, and we know that's little Endian. So we read that in, that's absolutely fine. And we're writing it into this data thing on our platform. So this data is technically now big Endian, but because of the way I've written it, it doesn't actually matter because we're reading one bit at a time and just putting it in the right place. So this whole big Endian thing that I said here is a lie. We don't have to handle big Endian there because we've technically already done it. So we would have to do it if we'd had taken 2 bytes out of memory in one little chunk. We would have then had a word encoded in little Endian and then just kind of wrote it into a word on our platform. That wouldn't have worked. But because of the way it's done here, reading 1 byte at a time and then incrementing the program counter is actually totally fine. That totally works. So that's just a comment change there. I'm just lying to you saying we had to handle big Endian, and actually we don't. So what else was there? Yeah, so one of the other things was, when I left it in the last video, I had some to-dos here about why are we consuming these extra cycles. So we've got a few instructions that, I think this is the one I've got here. Store accumulate at absolute X takes 5 cycles. But if I look at absolute X on something else, the ones we've done before, oh, this is add with carry, we've not done that yet. And yeah, load accumulate is one we've done. And this was a weird one because this is the one we wrote for, which was So yeah, this absolute X, this is the one we wrote for originally, we tested, and this one's got this magic, like it's 4 cycles, but maybe it's an extra one, depending on if we cross that page boundary. And we reused that addressing mode to do STA indirect Y, I believe. STA indirect Y. Well, let's look at absolute X. There it is, STA absolute X, there's the one. So that one's just a blanket 5. So these behave differently. And this probably explains why I had to have this extra cycle going on down here, because in here we didn't consume, in this addressing mode here, we didn't consume the extra cycle, but we should always consume the extra cycle in this particular case. I don't know if I just add a different addressing mode for this, which is like a version of this that always takes 5. Like in this one, it would basically be this, I think. I think that's where the extra cycle's coming from. I think it's like this cycle's always consumed on this addressing mode on this one. But of course this has to have a different name. I'll just call it, I don't know for now. I'll just call it 5. This is like the 5 cycle version. I think, is it only ever used here? And it's 4 plus 1, 4 plus 1, 7. So that's different as well. 4 plus 1, 7. 4 plus 1, 7. 4 plus 1, 4 plus 1. Am I going around here? I'm not sure if I've wrapped yet. 4 plus 1, 7. So we've got these weird, this is the only one that takes 5. So maybe like me trying to do this is like subtracting the correct ones. Like it appears that like this is the only place that this takes 5 cycles. So I don't know. I think I'll just roll with it for now. I don't really know what to call this. It's just like always takes a cycle for the X page boundary. Again, we'll just roll with it for now and then see what we get. But I think this might be the way to do it. CSTA. Yeah. Okay. Right. I think that's right. So where was that used? STA absolute X. So in theory now I just do that there instead of that. Get rid of that. I get rid of that. And we're still good. We've still got 39 passing tests. I think it's the same thing for this one. So why not? Let's just do it. Is this good idea to hang up at the moment? So this is already becoming harder than I thought it was going to be. But that's the thing, when you're writing a program, you don't really know where it's going to go a lot of the time. Even something like this, you think, oh, it's simple. I just implement all the instructions, and then you find out they're all got weird addressing modes, and all the addressing modes are always different depending on, because you're trying to emulate a piece of hardware here, so it's not behaving like a piece of software would. Always takes a cycle for the Y page boundary, C STA absolute Y. Right. So that fixes that one, does it? So we're getting rid of some of our to-dos. Cool. And the other one is indirect Y, STA indirect Y. Is that also, yeah, it's either 5 plus 1, but in the case of this one, it's just always 6. So I think I'm going to do the same thing. I'm just going to put 6 on this one down. Again, I think it's as good as an idea as any at the moment until I know what's going on here, but at least we've got like kind of a reference as to what this is going to do. Always take cycle for the Y page boundary, C STA indirect. Right, get rid of that, get rid of this, get rid of this. Well, That's an improvement, probably an improvement. Who knows? Maybe I've just made it worse. I mean, all these look all uniform now. That's not necessarily a good thing that it's all nice and tidy like that, but anyway, that's kind of like, you can see it doesn't look like what we started with originally. These are different now. Does it still pass? So they still pass, so I've not broken anything, and that's the important part here. And then the next thing is I was looking at, now we haven't implemented JSR yet, but I was thinking that might be a nice place to go next, because I can now, basically because I've got LDA and STA, I can load something out of memory and I can store something into memory. So I can do that quite a lot. I should be able to write, in theory, a program that could copy a fixed piece of memory now. But I can't branch and I can't jump anywhere. So that's a bit of a problem. And that's why I put JSR in originally, but we kind of just put it in quickly and didn't really do very well with it. So what would be nice now is if we could get all the jump and instructions done, and then I could jump around in the code. But if I want to jump around in the code, what I need is the stack working correctly, because when you jump around in code, you have the stack pointer, it pushes the stack pointer, it pushes the current program counter onto the stack, and then when you return from this subroutine, it will pop it off so it knows where to go back to, that kind of thing. In fact, that's what it's doing here. It's writing the program counter -1 onto this. It's writing onto the stack, and then it's doing this. Now the problem with this is it looks like I did this completely wrong, because this website actually does mention the stack on here somewhere. Stack operations. Here we go. So the 6502 processor supports a 256 byte stack, fixed memory between locations 100 and 100 FF. It requires a special 8-bit register. So that would make sense that if you can only have 256 byte stack, why not make it an 8-bit register? This is an 8-bit computer, so that would really help things along. But I think my stack pointer, I made it a 16-bit pointer because that would allow me to address anywhere in memory, but the stack can't be anywhere in memory. So that would make sense that the stack in the 6502 cannot be moved somewhere else. It's not like a thing on a modern processor where you can have your stack anywhere you want. It's just got to be there. It's got to be in that location, because it can't be in the 0 page, and it's just been decided it's in the 1 page or the first page. This is not a word, and we shouldn't store it as a word, because it isn't in the actual processor, I think, and that might affect how it wraps and stuff like that. But if I do that, whenever you try and access something from the stack pointer, you can't just promote that to a word, because you'll have the wrong address, because it's actually in the 1 page. So I need to, like, whenever we use that, promote it to, oh, it's the stack pointer in the 1 page. Is it called the 1 page or the first page? Is it the 0 page and the first page? I don't know. So it's called something like that. So I'd really like to get that working. Oh, this is something else I got wrong as well. It says pushing a button to the stack causes the value to be stored at the current free location. Then the stack pointer is post decremented, which, if you look at my JSR, is not what I did. I think I initialized the stack pointer to the 100 position, and then I'm incrementing the stack pointer. So this is clearly wrong. So that's a problem. So I think what I'd like to do is, now we've basically got all that working, load and store operations. I think rather than doing the stack operations, if we just got here we go, jumps and calls. This is what we need to jump about in the program. We just need jump, JSR, and RTS, and these two are kind of a matched pair, because when you JSR, you then RTS. And so that's jump to subroutine and return from subroutine. So you go in, that needs to push and pop the stack, and jump just goes to that location and you're just there forever. So that probably doesn't need to access the stack, that one. So JSR is the one. Yeah, and I think we looked at this before, pushes the address -1 of the return point onto the stack, then sets the program counter. I think we should do maybe I'll write a set of tests that can do a JSR, that can do JSR. Well, is there any point in testing JSR on its own? What can I really test from that? Because if I jump to a subroutine, I could probably jump to the subroutine and know that I executed something there. Did I already write? I don't think I wrote a test for that originally, did I? But then I'd really need I really need to test these as a pair. I need to be able to jump to subroutine, return from subroutine, and then maybe execute the next instruction So maybe I'll tell you what, I'll create a set of unit tests to do jumps and calls. We'll call it that, because that's what's going on here. So we'll do the jumps and calls next, and then we've nearly got enough stuff to write a program. So let me make a new file for that now. So yeah, I've just made something called jumps and calls tests. So it's just a copy of what we had in there before. Now I'll just remove, because it's a copy of that file, I'll just remove everything that I don't want. Could I really use that? Verify and modify flags. Does that modify? Yeah, so we can keep that test actually, because this doesn't modify anything. So we'll keep that in there. So this is going to be called jumps and calls tests. And I'll tell you what, let's just copy one of these and kind of use it as a starting point. Let's get rid of all this stuff. So what we want to do is write a little program in line that can jump to a place in memory, jump back, and then just execute one instruction. And I think that's all we really need to do. So this one would be, this would just be can jump to subroutine and jump back. And we can verify we jump back, like I said, by setting a register, because we've got stuff that we know works there. So we are kind of doing the RTS there at the same time, but this will be one good test to actually get this working, I think. So let's clear that. So this is our reset vector. It's JSR, isn't it? Instruction JSR. So we want a JSR, and it's only got absolute dressing mode. It takes 6 cycles to do that. So we'll need at least 6 just to do the JSR. And we need to jump to an address. So let's jump to, I like jumping to 8,000, I don't know why. So remember, little Endian. So that's the absolute addressing mode, that's correct, isn't it? The full 16-bit address of the target location. So that's what we do. JSR, jump to 8,000. And then in 8,000, we'll put an RTS. So in theory, that just returns us back to where we were. Don't know that RTS has any. Shouldn't do anything, should it? RTS. It pulls the program count of -1 from the stack. Implied addressing mode, and that takes 6 cycles. So it's 6 plus 6. Implied addressing mode means there's nothing to do. Source and destination is manipulated. Yeah, no further operations. So there's nothing to do on that one. So yeah, 6 plus 6. And then we'll technically should return back to the program here. C, D, E, F. Oh, we've run out of memory here. We're about to run out of memory. We're about to go off the end, but that's fine. Because we've got space for one more instruction here. Oh no, we haven't got space to do anything. So that's a problem. We technically run out of space in our reset vector there. In fact, one of the things I did is I can actually reset the CPU and I can actually give it a reset vector. So that's something I'm going to do now. Let's give it, let's go from there, FF00. So I can actually reset. I've actually changed that function slightly so that I can actually have my own reset vector. There we go. So we go from 1, 2, we jump to 8,000, and then in theory I'll just carry it on like this, and then it returns, and then at 3 we can do an LDA instruction because we know that works now. We want LDA immediate, and at 4 we will have the value that we want to put into the A register. I'm going to put 42 and hex in. Wow. So LDA, we need to just look up how many cycles we need to do this, because we've got to run that. We know that's 6. We know that's 6. And then LDA immediate. LDA immediate needs 2 cycles. So in theory, this can be done, and out of the end of it pops the 42 into the A register. So that is actually very good. I suppose we're not verifying these unmodified flags here because we need to verify them after the JSR. I mean, I suppose this is where you could execute some cycles, stop after the JSR, and do that. We'll do that in another test. Right now, I'm doing a bit of a combo test, is that I want JSR and RTS to work. What I need to test really is that the stack pointer works. That's what I'm trying to do here. So I don't care that it might be writing to the wrong place in memory if I did a test like this, but at least I know that you can push and pop from the stack. So I'll execute all of that. I will expect all the cycles to be consumed, and then I expect the A register to have 42 in it, and I'm not going to do any other verifications on that. That, in theory, is a good test, I think. Except I need to define this. Just put these down at the bottom. Where's RTS? And it's not real-time strategy, it's return from subroutine. Opcode 60. Right, does that compile? Verify modified flags, unreferenced local function. I will just get rid of that for now. And let's assume that we're never going to need it. Boop, there we go. So that clearly doesn't work, but that's because we didn't actually implement RTS. We kind of implemented JSR, but we're not implementing RTS. So this is only one test. I think we're going to need a lot more. Again, so actually, maybe while I'm here, I'll have a quick stab at doing this. First thing is the stack pointer. Well, according to the docs, the stack pointer needs to be decremented. Yeah, 256 byte stack. So the stack pointer is decremented, not incremented. That's one thing. Second thing, the stack pointer is a byte, it's not a word. We're going to do that. Right, this has caused a lot of errors already. So yeah, next problem here. This bit is assumed, this 0, 1 is assumed that the stack is in this one page. And we don't initialize to 0, 0, we initialize to FF, I think, because we're going to decrement this. So we're going to move our way down in memory, down to a lower address than a higher one. So that's the first thing. Oh, that's fixed all the problems. Okay, that's fine. Now the next problem is, I'm trying to write a word here to the stack, but this won't work because this is now the wrong address, because this is a byte. So really, I need to take this out and make like a push stack thing. Whoops. So what I really want is, well, this is just pushing the program counter to the stack, isn't it? So this is void push PC to stack. Don't know if this is going to be a common operation. So in theory, that's what this does. I'll get rid of this comment now. We need to promote the stack pointer to 16-bit. Now that might be something that I want to make a function for as well. Yeah, I think it's that. Yeah, so that's just promoting the stack pointer to an actual just 16-bit address. Yeah, I'll just call it sp to address. So it gives us a full 16-bit address. So the stack pointer as a full 16-bit address in the first page. Yeah, I think that's it. So now when we write this word, that's the address we write it to. We have to convert that to a full proper memory address. So this is push the program counter -1 onto the stack. Yeah, I think that's right. Needs the memory. Okay, so now we can replace this down in the here. So we can replace all this. Is that right? Push PC to stack. Did said I wasn't going to write any code this video, but here we are doing it. So is that right? Is that what we do? Yeah, so JSR fetches the word to be, which is that's the address that we want to go to, pushes the program counter onto the stack, correctly we think. Then it moves the program counter to where we want to go to, and we take another cycle for doing that. So in theory, that is JSR working, but this still doesn't work because we're trying to jump back again. So we really want now to find out what the hell does RTS do? Well, we want to write RTS. So RTS, what do you do? It's it pulls the program counter -1 from the stack. So we want our stack pointer to address. So we want to read a word. That's right. Whoop, read world from the stack pointer, which is in memory. Yep, that's it. So this is the RT return return address. Pulls the program counter -1 from the stack. I mean, it doesn't feel like that's right though, because we've pulled that. We need to pop the stack as well. That's the other thing. Yeah, so why don't we write a function for that as well? Because it's kind of this. This is pop program counter from stack. Is it really? It doesn't really matter that it's the program counter. It says pop address from stack. Let's say pop word, because it doesn't have to be an address. It can be a thing. Right. That's the value from the stack. So we read a word and we want to increment the stack counter by 2 because we're popping that. I think that's right. There we go. So that takes the cycles into account. And then it feels like we're at, why are we at -1? The program counter -1 from the stack. Feels like that doesn't work. I mean, maybe it works in the actual processor, but it feels like here it doesn't work. Is that right? Because we fetch the byte and then we increment the program counter? Yeah, I don't think this will work. But let's just run it and watch it fail. Yeah, that failed. Instruction 0 not handled. Oh, it didn't fail in the way I thought it was going to. Oh, that's a problem. Yeah, actually, here's a thing. RTS consumes 6 cycles. Holy cow, what does it do with all those cycles? Who knows? It takes 1 to read the instruction. There'll be 2 to pop the value from the stack. There's probably another one. There's probably another one to change the stack pointer. Yeah. And then is there another one? Is there another one to actually take that address? Oh, it's probably 2 more there. I reckon it's 2 more to take that return address and copy it into the program counter. Could be. We can just have a look at that quickly. There's only going to be 1 RTS in here. So it took 1 to read, and then if you go down here, it was on 7. That was 3. So it's taken 4, and then 5, 6. I think that's right. What did we get? Failed. So it's kind of what I expected, but I didn't expect this instruction 0 not handled. It might be because it's going back to the wrong place. I think that's actually what's happening. It feels like we're supposed to be here, but that's not right either. So let's just see if we get the right thing off the stack to start with. The return address is 000. That's not right. That is not right. So we can have a look in memory and oh, we already got it there. So it's a good thing about the memory here is we know exactly what's supposed to be in the memory now. So we're looking for the first page in the FF place. Oh, have I already popped? I might have already popped this. I suppose the stack doesn't get erased though. Where are you? FF. So doesn't look like we got the right values in there. We're putting 2 and a 0 on the stack. That seems wrong. Let's just run that again. Oh. This is where I could do with writing the debugger next. So here's the stack. So we're expecting it to write here and here. We're expecting to write the... It wrote nothing. Oh no, hang on. Yeah. So... Oh, wait a minute. Yeah. So we want to push the program counter to the stack -1. That's when it's going to write it, because that's the address that we're going to. So FF02, that's right, isn't it? I think that's the address we want it to go to. Oh, wait a minute. We're in the wrong place here. Why is it writing there? It shouldn't be writing there. What's happened? Again. So stack pointer is FF. Oh, wait a minute. Yeah, because we've got to write we're writing 2 bytes. And we have to write 2 bytes little endian, so we have to move back 2 bytes on the stack. Oops. So, in theory, this is stack pointer to address -1. And then if we want to read a word back from the stack, well, let's just deal with that one for now. Because this could just go horribly wrong. Right, push program counter to stack. Oh. Yeah, I thought it did look a bit dodgy. So expecting it to write there. Yeah. So we write, so that's little endian word has been written onto the stack. And then the stack pointer is, what's our stack pointer at? FD. That kind of makes sense. And then we go to there. We come out of here. And the return address is 200. That doesn't seem right. So I think we're getting a little bit further. So we just need to get this, pop the word from the stack. I think this is the bit that's wrong now. So the value from the stack is 200. That's not right. I think we've got to go. Is it up to, where are we going to reading that? We're currently at that address. Let's try that again. I don't know if that's right. So the stack point is at FD. Yeah, we don't want to read from FD. We want to read from the stack pointer to address +1. I don't know if this is the right way to do this. It seems very weird having this +1 and -1 in here. But let's just see if we can get the test to pass. Oh, can we get it to pass? No. Instruction 128 not handled. So something's gone weird there. Let's see if we pop the right address though now. FF02, that seems right. And then we fetch the next byte from FF02. Is that wrong? Oh, well, for one thing, the test's wrong here. Ooh, that should be that. I've overwritten. It should have been 1, 2, 3, 4. I think we're jumping back to here, though, and we should be jumping back to here. So I think that's the next problem. What? Instruction 128 not handled. Is that the right window? Yeah, I think we have to go to there, return address +1. Whoops. Yeah, I think we have to go to return address +1. Oh, that's it. Well, it's probably it. So that is all a bit crazy. It's just that why do we? I think we push the program counter -1 because maybe I'm doing this fetch byte wrong. Maybe I'm supposed to increment the program counter then fetch the byte. So that's definitely something worth considering. But this is probably right. I think we'll roll with it for now, but we've got an instruction that can pop a word from the stack. And we've got something that can actually push the program counter to the stack. Which makes sense that we want to be able to do that. Push the program counter -1 onto the stack. Yeah, so I think I'll leave it there. So that's pretty good. So I've got JSR, probably got JSR and RTS working a little bit better. I think next time I'll just write a lot more tests for this to make sure this whole thing works. I think we need to be really sure that know what we're doing here with this program counter -1 and how this program counter actually works, whether it's I come in here, I increment the program counter and then fetch a byte, or do I fetch a byte and then increment the program counter? So I need to do some more investigation into that and find out if that's right. But as far as it goes here, there's only one more test there, which is can jump to a subroutine, jump back again. But that's not bad, I think. Anyway, so I'll move on in the next video and see how much further I can get and investigate whether I'm actually doing this right. If I'm doing that wrong, that could mean a lot of the tests could be broken if I change that. In fact, just for a laugh, if you change this, you get to see how much testing this breaks if you just like do something like that. And the answer is, that's what would be broken by changing one line of code. And the answer is 39. God, did we get a test that passed? CPU does nothing when we execute 0 cycles. So we got what that fails every test if you move one line of code. And that really shows how crazy this is. There we go. So back to 40 tests, but maybe if we do enough, we'll break this in the next video.